Hello, in this video we're going to be talking about atomic orbital theory. This is a more advanced way to think about how the electrons are arranged inside an atom. We need to go back in time a little bit to the early 20th century and talk about Bohr's contribution to atomic theory. So Bohr said that the electrons inside an atom orbit the nucleus in the same way that the planets orbit the sun, and it was called the solar system model. So if you imagine that this would be the sun, the planets going around in discrete circles, and so Bohr's model was proven incorrect because it didn't explain a lot of the properties that matter has. So one of the bigger questions of the day was, if you take a piece of iron, which is an element and it's a metal, and if you heat it up beyond a certain temperature, then it starts to glow. So why does that happen? So as well as of a lot of experimentation that was happening, a lot of the development of modern physics, the idea of classic physics, Newton and Galileo had a huge influence on that type of physics. But then once people discovered the nucleus and subatomic particles, a different type of physics was needed. So that's how modern physics has developed. Another scientist developed the idea that electrons can exist as a wave or as a particle. And so Bohr's model doesn't explain why electrons can be particles and waves. So the theory developed, part of Bohr's theory that was correct was the idea that electrons exist in energy levels. We've called these rings electron shells for now, but that's actually incorrect, and we're actually going to start to call these energy levels. So the idea is that electrons have certain amounts of energy depending on how close they are to the nucleus, which kind of makes sense. If you think about these electrons are closer to the nucleus, obviously electrons are negatively charged and the nucleus is positively charged, so you've got more attraction if they're closer. As you move further away, these electrons have less attraction to the nucleus, and as you get even further away for this electron, it's got even less attraction. So all I've done for this diagram to this one is redraw these energy levels as straight lines and not rings. So this is the nucleus, and then these are the first two electrons, and then the next 8, and then the last one. Obviously sodium's got an atomic number of 11, so it's 2, 8, and 1. So Bohr's theory was that electrons exist in these energy levels. Where his theory was built upon was the idea that electrons can change energy levels, and if they jump up an energy level then drop back down, because they can't stay in one energy level unless that amount of energy is kept up. So as they drop back down, energy is given out, and that's one of the reasons why we get things like ultraviolet light, visible light, which is the white light we get from the sun on this planet, infrared, X-rays, microwave radiation, all result from electrons dropping down from one energy level to another. So the idea of energy levels. So other scientists contributed to this modern development in orbital theory. Two of the biggest people are Schrödinger and Heisenberg. If you watch Breaking Bad, Heisenberg is Walter White's alias. So Schrödinger decided that that electrons are going to be in a certain area. Heisenberg said you can't predict exactly where the electron is going to be in that area, and you can't predict its velocity. You can't do both at the same time. So the idea of orbital theory developed from Schrödinger, who used a lot of complicated math and a lot of advanced thinking, which is actually beyond this class. This topic would take a lot longer, and it's actually more of an advanced topic for college and so on. So Schrödinger, a lot of complex math, which we aren't going to talk about, but his idea was electrons exist in orbitals. Heisenberg said you can't predict where the electrons are inside an orbital. So this is where we are. We've got this idea that electrons exist in energy levels, and each level has a certain amount of energy. As you get further away from the nucleus, the energy increases. So maybe you start to see a pattern with the energy level idea, the first one holds 2 electrons, the next one holds 8. This one could hold actually 18. I'll explain why in a moment. But some of the ideas that we talked about from Lewis dot diagrams will transfer over into our discussion of energy levels and orbital theory. Before I talk about how the orbitals are arranged around inside an atom, and then how many electrons each orbital contains, the ideas that Schrödinger and Heisenberg came up with can demonstrate using a fan. So you can see where the blades are in this fan. As I turn it on though, you can't see the individual blades anymore, but what you can see is where the blades are, the area where they are. Right? As they're moving around, they take up a certain area, but you can't accurately predict exactly where the fan blades are at any one given moment because your eyes just can't pick it up. If you had a really high-speed camera and took a snapshot, maybe you could see the individual blades again. But really, this helps demonstrate orbital theory because the electrons are inside the orbitals, they're taking up a certain amount of room, just like the fan blades take up a certain amount of room, and then you can't predict exactly where they are. You know where they are, you can't just say exactly where they are. So if you think about orbital theory, as we move on from this more simplistic diagram, so this version will actually not be as correct as this version, but think about it simply as electrons take up a certain area, you know where the area is, but you can't predict exactly where they are. So I'm going to erase this and then talk about the orbital shapes that we know exist, and then how many electrons exist in each orbital. So a lot of work has gone into understanding the shapes of the orbitals, and mainly it's due to Schrödinger and his mathematics that has developed this theory. So again, we're not going to get into that, but we do know the shapes of the orbitals now, and that's actually where we're going to pick up 3 main orbital types that we're going to look at. There are more. Once you get to d orbitals and beyond, it's actually probably more college level, and we're actually going to stop at d for the purposes of this class. So s orbitals have a spherical shape, and that is a perfect circle, hand drawn. So s orbitals are a spherical shape, so the electrons are inside this orbital, moving around with lots of energy. You can't predict exactly where they are, but just like the fan blades, you know the area where they are. So if you imagine that you've got the nucleus at the very middle, and all the electrons are moving around in a sphere around the nucleus. So the s orbital has that shape. The p orbital has this like a dumbbell shape, or I suppose even a fan blade shape, but the electrons move around, go from one side to the other side. You can actually fit 2 electrons, oh sorry, this is 2 electrons, and inside one p orbital you can get 2 electrons as well. I'm back in 5 minutes. Sorry. So then the p orbitals can actually arrange around a nucleus. If you imagine that this is the x-axis, you can get another p orbital on the y-axis, and then you can get another kind of coming out towards you on the z-axis. So you've got the ability to get 2, then 4, then 6 electrons, in 6 electrons total in the p orbitals, and there's 3 of them, and they take this shape, kind of vertical, horizontal, and then coming out towards you. I'm not even going to try and show you the d orbitals because it's actually really complicated to draw, but it's kind of like a flower or like a clover leaf. there are better ways to show that, and 3D is a lot easier than me trying to draw it on the board. So in class I will show you examples of d orbitals, but they hold 10 electrons. P orbitals hold 6, s orbitals hold 2. Maybe you're starting to see a pattern here with the numbers that we've already dealt with, 2, then 8, then 18 if you add all those up. So there are some things from Lewis dot diagrams that will carry over into orbital theory. So those are the shapes for the orbitals. So what we're going to do now is look at a periodic table, and we'll relate some things that we already know about the periodic table to this idea of orbital theory. And the nice thing about the periodic table is it does actually give us some major clues. So, periodic table. So, periodic table, as you know, it's laid out in columns called groups and then rows called periods. So the first period elements have one energy level. Second period elements, so all these across here, so 3 through 10, all have 2 energy levels. Then 3 energy levels, 4, 5, 6, 7. Really nice that it's laid out that way. Actually, the way that it's laid out, that kind of comes as a coincidence, but we know that the period tells you the number of energy levels. First row has 1, then 2, then 3, then 4, then 5, and 6. We're not going to go much further than the 4th period, so 4 energy levels. It gets really complicated. This is more bachelor's level, right, in chemistry, so quite an advanced area as we go down through these 3. Well, we're going to kind of stop at the 3, 4 energy level mark. So how do we figure out the number of electrons in all these orbitals and how does it all come together? So if you can imagine the nucleus is in the middle, the 1s orbital, or the first s orbital, forms like a sphere around the nucleus. If you add another s orbital, it's going to be slightly bigger, so that will go around the outside, kind of like a coating, and then you'll fit in the p orbitals on the x, y, and z axis. So if we look at the first period elements, hydrogen obviously has 1 electron, it's got an atomic number of 1. So hydrogen has 1 energy level. So the way that we show that is with a 1, which is nice. And then we look at the number of orbitals that it has. If it's only got 1 energy level, or the first energy level, it can only have 1 orbital, and that's the S-shaped orbital. So S comes first. And it's got 1 electron, so we show that as 1s1. So this means first energy level, S-shaped orbital, 1 electron inside that orbital. If we looked at helium, which is the other element in period 1, it's got 2 electrons, so we'd actually show that very similar, but this time it's got 2. First energy level, S-shaped orbital, and 2 electrons in it. So we'll go down to the next period, which is the second one, and that's 2 energy levels. So for lithium, we start the same way because it's obviously got its first energy level. That has a 1s orbital. 2 electrons fill that up. So that's similar to the electron shell idea that we talked about earlier. That first electron shell holds 2 electrons. But we're not done with the number of electrons, we've got 1 more. So we need to add another energy level. So this stands for second energy level, and then the first orbital within that level is an s orbital. And then we've got 1 electron left, so that would be 1 electron inside it. So 3 electrons total, 2 go in the first energy level, 1 goes in the second, S-shaped orbitals only. So beryllium would be very similar. It's just got 1 more electron. So the s orbital only holds 2, remember, so if we go beyond beryllium, we've got to add another orbital. So if we have boron, because it's got 5 electrons, we actually need to add another orbital. So the next in series is the p orbital. So the way that these fill up, it's 1s first, then 2s, then 2p. First energy level, second energy level. So as far as the second energy level goes, we could actually add up to 5 more, and that would actually be neon. So 1, 2, 3, 4, 5 more electrons. So that would be 6. That would be neon. It's got a total of 2, and 2 is 4, and 6 is 10 electrons. And this is how the energy levels fill up. So this would be the first energy level, this would be the second. If we go to the next energy level, we've got to add another orbital, but this one's full. Okay, so 2p is full. So sodium would actually be 1s2, 2p6, but as you can see, it's in period 3, so 3 energy levels, so we've got to add another energy level, so that would mean a 3. Ooh, that's a crazy 3. So then we've got 1 more electron to fit on, so that would go right there. So, to kind of recap orbital theory, the idea is that the solar system model, electrons going around like planets going around the sun, is outdated and wrong. But what Bohr did give us was the idea of energy levels, electrons having a certain amount of energy depending on how close they are to the nucleus. Obviously the ones that are further away, they're at day camp, right, away from home, they're having a great time, living the dream, they're away from their parents, so they're free, they've got more freedom to move. Ones that are closer to home, closer to the nucleus, not as much energy. What else? So then Heisenberg predicted that you can't accurately say where, or it's impossible to say where the electron is at any given moment. So think about the fan blades going around, difficult to see exactly where they are at any given split second, they're moving too fast. But Schrödinger said, well, you can figure out the area where it will be, where the fan blades will be, and you can see that with the fan blades going around. So 2 major contributions. How they got there is using an astonishing amount of math that, to be honest, I don't even understand, but they did it for us. That's a much more higher level of understanding for chemistry, which we're not going to get to in this class, but we'll just cover the basics of modern atomic theory, and then in the next video what I'm going to do is talk about how orbital theory and bonding go together. Because as you well know, all these elements make loads and loads of different molecules and compounds, and then they all combine in different ways. So how does this orbital theory fit into that? So that's where we'll pick up in the next video.